Okay, so this talk is entitled Functional Algebra for Middle School Students. And the basic premise is that we can get functional programming into universal education, so everybody learns it in school. And the way that we can do that is to teach type signatures in junior high algebra class. We don't have to get down into bits and systems, just type signatures and how program refactoring, at least at the type signature level, is very similar to the algebraic equations that we manipulate in junior high algebra 1. I'm Chad Brewbaker. I work at Data Culture LLC from Des Moines area. So how can we get functional programming into universal education? So it's not just programmers who know about it, but everybody. And what languages did we use to talk about programs back before we had, physical business computers? Because the first physical business languages were like COBOL and ALGOL. How can we refactor code on like a napkin and a piece of paper without having to pull out a full IDE to be able to do code refactorings? And how do we prove that our code is correct? Because we know that we've done only operations that aren't going to do anything to change the meaning of our code. And the answer to every single one of those is junior high algebra. So a couple things in this talk. We're going to try to ignore a lot of the fancy terminology, so not really much category theory. We are going to use sums, products, and exponents. And what we're going to want to do, I think, going forward is try to teach our junior high algebra instructors just enough type signatures so that they can teach it alongside their algebra class. So we're going to use 3 languages today. The first one is the Haskell language. It looks a lot like algebra. It's easy to reason about. There's no random database calls inside of a method. You have to flag everything that does some sort of I/O with an I/O warning. And it's designed for maximum flexibility of abstract design. Another language that we're going to use is the Ruby language. There's a lot of existing projects out there that parents can do with their kids. It's kind of a Play-Doh on top of C. And it's designed for maximum flexibility for humans just to sit down and tinker with code and get immediate results. And the third language we're going to take some examples from is the C programming language. It's essentially a loosely typed machine instructions that you execute on the computer. And it's for maximum flexibility to say, this is exactly what I want the machine to do. So here is some function notation in algebra, Haskell, C, and Ruby. So the first one we have up top is we have a function f, and it takes 2 integers and returns a string. This is kind of what it looks like when in algebra class, a function signature. The second one is what a function signature would look like in the Haskell programming language. We have a function f. It takes a tuple of 2 integers, and it returns something that's of a type string. And this is what it looks like in the C programming language. We have something of type string, and that's what it returns. And then the function takes an integer A and an integer B. Ruby is a little bit weird. You don't put the type annotations on your functions. So in the long form, you have a function f, which takes 2 arguments a and b. And this is the short form notation, where I have a function, that's what they call it a stabby lambda, that takes 2 parameters, a and b, and then returns what's ever in this. And then you can assign that to a variable f. Just take your function and pass it around as a variable. So the first thing that we're going to talk about is subtypes. So a subtype is I have something of A or something of B. So the key word that you usually use is or. So in Haskell notation, I have this data type X, it's either something of type A or something of type B. And here's an example. So Sally is going to drink something, and it's either going to be coffee or tea. And so we have something of type drink, and the drink is either a coffee that she picks up or a tea. That's a subtype. And in the C language, we have things called enumerations, where we can just put a list of different things. Ruby has something called enumerable types, which they will work. They're not ideal. So sum plus addition. Product. Product with A and B. A times B. So Haskell has product types. We also call them tuples. So we have this type X, and it's equal to this tuple of A and B. And so an example would be Sally's dinner consists of a fruit and, keyword and, a vegetable. So type dinner is equal to fruit and vegetable. So she picks one fruit, she picks one vegetable. She has a pair of them, a tuple. So product multiplication. C has a struct type that we can pack things into, like tuples. And Ruby, we have a couple of options. It has an array type that we can use. We just have to be careful that arrays in Ruby can grow and shrink, where tuples in Haskell are of a fixed size, so we have to be careful that we don't mess around with the size of them. And also, Ruby can use classes a lot like the way that C uses structs, so where we can put these things in a class that we're going to call product, and then just assign that to this variable. And this is the key thing that they didn't teach you in junior high algebra class. Exponentials. So I have something from type A mapped into something of type B. And the way that we write that is b to the power A. So A is called the domain, or the input type, and B is called the codomain, or the return type of your function. And so this is what it looks like in Haskell. We have a function f, and it goes from A to B. And here's an example. Sally chops a carrot. Sally has a function called chop. It takes as input a carrot, and it returns a diced carrot. Once again, exponents are functions. We're going to talk about some simple values for some small things. The first thing we'll talk about is -1, square root of -1, or undefined. In algebra class, we call it irrational. We have a set of size 0. In Haskell, we call that void. We have a set of size 1. In Haskell, we will call that unit. And also, sometimes we'll just treat it as like an empty parentheses. Now, I'll explain why later. For sets of size 2, we call them bool. And for anything larger than 2, we just usually make up a name that sounds good for that use case. But bool is something that's pretty standard for sets of size 2. Okay, here's our first algebraic equation. Constants are functions with a unit as an argument. So on the left-hand side, we have this function foo. It's a, just like an algebra equation up top. And then we have the second function bar, which takes in one thing and returns an a, which is the same as a to the first. Remember, it's what's on top mapped to what's down below. So I guess maybe the way that you could interpret that is if I only give you one way to do things, if I only give you one way to do something, you have to do it that one way. And this is also a key concept that a constant is a function that takes an empty list of things. Yeah.
Are you saying that foo and bar are equivalent in this case?
There are many programs where you can refactor them as equivalent, yeah. With void types and units, it gets a little bit hairy. It works a lot better when you're dealing with product sums and exponents in general without sticking down to the smaller types. Another program refactoring we can do is we have tuples versus tuple lookups. So the equation we learned in junior high is a times a is equal to a squared. So let's rewrite that in function notation. Foo is a tuple of two a's, a times a. Bar is a function from bool to something of type A. And the way that we can interpret that in this thing up above is either I take the left A or I take the right A. That's what that bool tells me. Which of these A's do I pick out? And so if I have either of those pieces of code, I can refactor them into the other one. The void type, the empty set, it behaves a lot like 0. So if I have 1 is equal to a to the 0. So I have a function foo, which just returns the unit, one element set. That's the same as the function bar, which takes an empty set and maps it to something of type A, whatever A is. Also, a times 0 equals 0. That's the same as saying if I have a tuple of something and something which is void, it's a set of 0, it's not really there. That's really just the same thing as saying void. And it also works for sums. So if I have a type that's A or void, I can just ignore the empty thing and just simplify it as A. And this is probably isn't something that you would necessarily teach to a junior high algebra student now, but it's something that we could start teaching, because once you start getting into small functions on finite sets, you can talk about even things like calculus without having to get into infinite series and stuff. I can say I have this derivative with respect to x of a times x to the n, and that's equal to a times n times x to the n minus 1. So the way that I would explain this to a junior high kid is I have this data type n, and it's equal to m or one extra thing. So if I have n and I remove one element out of n, this 1, then I get m. So m is something that's one thing smaller than n. That makes sense. And so if I take the derivative of n, what that gives us is this of a, and this is actually just a tuple. Get this, and it works out. Yes, I don't want to get into the, but no, I mean it's the same rules. Currying. We learned currying in junior high algebra. So we can pass an argument list, or we can chain functions. So on the left, I have this expression of a to the m, and then that itself is taken to the nth power, and that's equal to a to the power m times n. So curry foo is a function from n. Remember, you take the exponent, that's the input type, to another function's return, m of a, that's what's inside the parentheses. And then on the left-hand side, we have these two input arguments smushed together into one tuple, and they return this one element A. And here's some working Ruby code that's the same thing. So I have a function foo. It takes two arguments, n and m, and it returns them in plus. In Ruby is the same thing as string concatenation. It's overloaded. So if I call foo on thing 1 and thing 2, it just smushes them together and prints out thing 1 times thing 2. And then I can refactor this. I can say foo.curry. And what curry does in Ruby is it says whatever argument is the first argument, take whatever value I'm giving it and put that in as a constant. And so every time that I call bar, the first n there is always filled in with thing 1. It's always implicitly filled in. You just have to fill in the second argument. So we'll fill in the second argument with thing 2, and it prints out the same value. So with currying, we can either pass in a tuple of arguments, or we can chain functions together. I'm calling this co-curry. There might be another name for it. So if we have multiple function calls, we can also combine them into a tuple. So we have co-curry foo, which is a pair of 2 functions. The first one is m to a, and the second one is m to b. We can combine those two, smash them together into something that is m and returns both a and b. So here's what it looks like in Ruby. I have foo is equal to a list of 2 functions. The first function takes an element m and returns m plus m. The second function just returns the identity m. It's a list of 2 functions. And so it prints out a list of where the first function of the foo list is called with thing, and the second element of the foo list is called with thing. Same thing. And so the first time it prints out thing, and the second time it prints out thing. And then my second function bar, it just takes in 1 argument, m, and it returns a tuple of the 2 functions that we're applying to it. The first one, it just repeats the thing twice. The second one, it repeats the exact same thing. So I get thing, thing, thing. Also, we can split function inputs. So the algebraic identity a to the m times a to the n equals a to the m plus n. So we have this data type b that's either of something of m or it's something of n. And we have a function foo that is a tuple of 2 different functions. The first one has inputs of type m and returns an a. The second one has inputs of type n and returns an a. And this function bar, what we've done is we've taken that m and that n and smashed them down to this big type b, and we're able to pass everything through that. So for foo, we pass it an even number, and it just returns it. Or on the right-hand side, we pass it an odd number, and it returns 2 times the odd number plus 1. And then we're going to print that out by calling the function on the left with 2, and the function on the right with 3. And we get the results 2 and 7. For bar, we only give it 1 input, x, which is able to take both evens and odds. And if it's x mod 2 equals 0, meaning it's even, then it just returns the value. Otherwise, it returns 2x plus 1 if it's odd, and we get the same result. So that was, we can split up our function inputs if we want to. Division is a little bit weird. The way I best describe division is essentially ignoring things. Saying divide by x is, I want to ignore things of type x. So on the left-hand side, we have a to the m divided by a to the n equals a to the m minus n. So m is this data type that's either a b or it's an n. So it's split off into 2 things. And so we take this whole function m a, and we remove just the things that where it gets inputs from the n. But we keep things that are inputs from the b. That's the same thing as saying, well, let's just write a function that takes stuff from b to a. Let's not worry about removing it. Let's just actually remove it in the type signature. So here I have a function foo. It takes an input x. X is even. It's like error. We're supposed to be ignoring these. You weren't supposed to call me with this. Otherwise, it returns 2x plus 1. And we call it the 3. We get back 7. And then we have the function bar, which just expects that you never call it with an even number. And just prints 2x plus 1, it's 7. Another thing that we can do is we can suppress some outputs or shrink the output type. So a to the m divided by b to the m is equal to a divided by b to the m. So we have this data type a, which is either an n or a b, and we have this function that acts from an m to an a, is this whole big thing, and we remove everything that's going to have output type b. That's the same thing as saying, well, let's just clean that up in the return type by just only returning the n side of that, and not worrying about filtering out the b outputs. And you can go on and on. This is just take a junior high algebra textbook, look up any of the exponent laws, the associative laws. Almost all of those go into type signatures of functions. And we can use this on more than just that. We can expand this to things like Fermat's little theorem. So Fermat's little theorem says that if a to the n minus a is divisible by n, always when n is prime. And so if we refactor it a little bit, we have this expression a to the n is equal to n times k plus a. And so a to the n, refactoring function looks like that. And the right-hand side looks like this. And so whenever the set n is prime, there always exists a program refactoring that allows to do this. It's a good thing to know. And it also tells us about program refactorings we know that are impossible. Fermat's last theorem. X to the n plus y to the n equals z to the n has no solutions for n greater than 2. So if I have this function foo, that's either a function from n to x or a function from n to y, and I have this other function over here that my manager wants me to refactor it into called bar, which is this really simple function that just takes n to z, I can tell him there's no way to do this when n is greater than size 2. Fermat's last theorem.
If it's that straightforward,
Say that again?
if it's that straightforward, like, why did it take a really long time to prove that? If it's like the types say, oh, you couldn't possibly.
Actually, if you go back and you look at Weil's paper, he actually uses a lot of category theory. Like you'll see like category theory diagrams. And I would suspect that we still don't know the simple thing that's going on there at the type level. That still hasn't, I mean, he chained together a bunch of different results. And I still think there is a type explainable proof out there. But we just haven't condensed it enough yet.
Some things are intuitive.
Yeah, well, a lot of things are still in category theory speak. We haven't simplified them enough to functions on finite sets that. And also, I mean, this is something that we could go on to teach to extend things in like the high school curriculum where we're dealing with more complicated equations. So we have the binomial theorem. We want to refactor between a product of sums and a sum of products. So we have this function foo, which takes a bool and it returns either an A or a B. I can just plug and shove the binomial theorem on it, and I can expand it out into a bunch of different cases. Like this is if everything is, if both sides are on A, if both things are B, or I have one A and one B, but I have to decide which order the A and the B are in. Sometimes those refactorings are useful. So some tips on how to read algebra as a programmer. N to the n is all the functions from n to n. All reorderings are n factorial. Let's ignore some stuff that's type x. So divide is kind of like, let's ignore this stuff. So here is, let's ignore reordering. And the sum symbol, let's give a stream of things. Product, I'm about ready to give you a large tuple, like here's all the things in my database row. And moving forward, I think we can teach our junior high algebra teachers just enough about basic type signatures to where they can start doing functional programming alongside algebra. The thing that we have to drive home is that functions are exponents, and there's going to have to be more practice problems on towers of exponents. I have bonus slides with monads. You need tower of exponents. Also, abstract algebra uses so much terminology, it can be kind of obtuse. You need to be descriptive and use more concrete examples. And also, I have a personal research project, Endoscope, that's about inspecting the structure of finite functions. Because right now we're still relying on too much intuition about what we think a function is instead of actually chasing all the different ways that a function applies itself and looking at the structure. Questions? Yeah?
Can we see the bonus slides?
Yes, that might be better for the hall track. I've got one bonus slide on if you want to do tree data types, and another one on what monads look like. I think the monad one might be interesting. I'm not going to play the code here. So if you actually take a monad and you write it out in the exponent notation, these are what the different laws look like. And you notice very quickly we're running into towers of exponents, and we didn't have much practice dealing with that in junior high algebra class. So this is something that we're going to have more practice problems on.
What's the subscript in this case?
The subscript?
Yeah, like your M subscript B.
Oh, that's like the bind operator for monads and stuff.
Oh, okay.
So that would be the inner type?
Say it again?
So the A or B, that would be the inner type?
Yeah, it's the same. So A to the B, a function from A to B, just refactor that. Yeah, and the M is that monad thing, like IO or whatever out in front. Sorry. Any other questions or?
Are there?
Yeah.
I don't really understand why functions are exponents.
Okay. So I have 2 items. Bool, set of size 2. And I'm going to say there's 30 people in the room. Set of size 30. So a function from 2 to a set of size 30. I'm going to give these 2 things to 2 people in the room. I can give them the same person if I wanted. I'm just going to hand them out to people. How many ways can I do that? How many different functions are there? It would be 30, everybody, to 2. I take those 2 things and I map them to the 30 people. So that might be the explanation, is that whatever top is the input, and I'm mapping that down below to what's in the output. And combinatorially, that's how you think about it.
You think of the 30 people coordinate form? Like X is the first person, Y is the second person?
Any other?
And then you,
Yeah, do you have exercise problems for all these different?
I don't have exercise problems that are written up. I would suggest just getting any junior high algebra text, going through the exponent laws, going through like the distributive laws. You want to pick up this concrete mathematics book, take any math equation in there, write it into the type signature of your favorite programming language.
What is towers of exponents?
So it's a function that returns a function that returns a function that returns a function.
Is it? It's not a read. Is it? I was just trying to find.
Well, I guess we're not good at like when we're dealing with lots of exponents that are in succession. Like we just, at least I never had much practice with that in junior high, and so that's why some things like like type signatures of monads and stuff, they look a little bit foreign because I'm not used to dealing with them. If that makes sense.
And what's the B in notation there? Subscripts? What is the subscript?
Yeah, I'm sorry. So with monads, you usually have this little identifier out here that's like, hey, I'm a monad.
Oh, it's just it's two different monads? Like MA and MB are just
I'll track. I can explain it to you later. Yeah.
I was wondering, you're talking about primes in there. Is there like, do you have an intuition like what prime size set would be?
Yes, I can. So back with Arthur Cayley in 18 whatever, he had the first paper on abstract algebra, and he put up a multiplication table. And he's like, hey, I can take these abstract things and I can come up with a multiplication table of them. And this is kind of cool. And the problem that I think we've had since then is that we're like, oh, well, permutations are nice because those are functions where they're always invertible, we never blow things away. And so where primality comes to play, at least in permutations, which are the simple functions to deal with, because I can always reverse them, you take a permutation function, and you keep on applying it, and it ends up in a cycle. And that cycle breaks out into a set of primes. And that's kind of the essence where the primality comes with. In my endoscope project, what we're dealing with is not just permutation functions, but all functions. There's other functions out there where, like, I'll take the thing that's number 2, and I'll put him on top of this guy, and I'll blow this other guy away. And so you have these trees where it blows stuff away, and then it enters that cycle once it becomes stable. And we're not really good at explaining all of those non-permutation functions yet, just because we haven't sat down with the computer and played with their structure yet. I could probably, there's a paper I can show you too, which actually goes through Fermat's little theorem. It shows you some stuff with fixed points and primality that might give you some more intuition. But yes, we're going to have to do more with factoring, because you can't have fractional, like what's a half of 3.
Oh, is that a question?
Say what? Oh. Yeah, I think our time's about up, so. I'm sorry, I'm like half deaf here. Yes, well, let me pull up that one key slide again. Yeah, well, let me put up that one slide again, because I've already gotten 2 questions about that. And I should have emphasized it a 3rd time. This is the slide. So function, in exponent form, in algebra looks like that. And in function form, it looks like this. Oh, the green one?
Sorry? It was like 6 slides, and I wanted to break them all down.
Oh, yeah, GitHub.com /Chad Brewbaker. I have my slides up there. I think it's called functional algebra if you want to pull them down. So.
Where could we get a list of like papers? Like, what do I search for?
Actually, I forgot a slide. Oops. Yeah, here's a couple of papers that you might want to look through. There's the original paper by Haskell Curry, where he kind of talks about how mathematicians should think about functions. There's a paper by Eric Wagner called Categories, Data Types, Comparative Languages, where he kind of focuses on sum types, product types, and exponentials. That one's kind of hard to find. You might have to go to a research library. Doug McGilroy, who actually spoke here last year, has a really good paper called Power Series, Power Serious. That's a good one to look through. And also Chris Taylor did a similar talk to the London Haskell group, I want to say, called the Algebra of Algebraic Data Types. That's another good resource.
I have one more question. What is your background?
I'm a combinatorialist that's a professional software engineer.
Combinatorial.
Yeah, I only have one publication. It's a generalization of Fermat's. I can show you later. But basically, I take all the 0, 1 matrices and you view it as an image that's black and white pixels. And then you kind of like take an X-ray. So like you have row sums and column sums, how many black pixels there are. 1 is black, 0 is white. And I counted how many images you could exactly reconstruct if you just have the row and column sums. And that turns out to be a generalization of polynomials. But that's a whole track thing. And